Morning, guys. So I hope you have understood a little bit introduction we have taken regarding the mechanical properties of fluids, right? I hope you remember we stopped with the topic relative densities, right? And I told you this and all is not present in your textbook. It is something which I have introduced or I am writing from my side with the need perspective or any entrance examination perspective. So we are going to continue from here until we reach pressure, right? I will take pressure topic, which is also a very small topic. So when we reach pressure only, actually your NCERT textbook topic starts, right? So we dealt with the equation for density, right? And we wrote mass by volume, and we dealt when there is a binary fluids are mixed in a container. So what and all will be the equation when we are mixing equal amount of masses, right? And we talked when we are mixing two fluids which are of equal volumes, right? I hope you remember the equation for the density for them, right? Now the next section is specific weight. Specific weight, the term which you have to learn, which is specific weight. It is defined as a ratio of weight of a substance to its own volume. That is, weight of a substance to its volume is known as specific weight. So weight, I can write it as mg divided by v, right? So m can be written as rho, density into volume into g divided by volume. So volume cancels out. So I can write specific weight is equal to weight or by volume. Also it is density of volume or object into acceleration due to gravity, right? So actual, what is the definition of specific weight? Ratio of weight of the substance to its own volume. And another equation which depicts a specific weight is density of that substance into acceleration due to gravity, right? This is one of a common term which you have to learn. And the next term which you have to know is specific gravity. We just talked about specific weight. Now we are going to talk about what is specific gravity, right? Specific gravity is defined as a ratio of specific weight to the given fluid to the specific weight of an equal volume of pure water at 4 degrees Celsius. That is, you are comparing the specific, so that is, this is specific weight or specific weight of a substance. Let's say I'm going to take a liquid. So specific weight of a liquid, let me write like this: specific weight of liquid when I compare it with specific weight of water, right, at 4 degrees Celsius. That is known as specific gravity of this liquid. This is just like we talk about relative density. Someone asks you what is the relative density of a liquid. It is what? Density of that liquid compared with the density of water. Similarly, someone asks you what is specific gravity. It is specific weight of a liquid by specific weight of water at 4 degrees Celsius. Right, so we just found the specific weight of any object is equal to density of that object. So this is a liquid, so density of liquid into acceleration due to gravity. Then specific weight of water also can be written as density of water into acceleration due to gravity. G cancels, so I can say density of liquid by density of water. Now you see that this is same, right? So usually some of the time we can even say specific gravity and relative density are quite similar, right? Because it is numerically equal. It is not actually same, right? The term, when you go talk about definition, it is different, but their magnitude comes up or same. That is, relative density and specific gravity of a liquid is numerically equal. Clear? Keep that in mind, right? And someone asks you, is there any another definition for specific gravity? Yes, there is another definition for specific gravity, which is weight of an object in air by weight of that same object in water, right? Obviously at 4 degrees Celsius. So another definition for specific gravity is weight of an object in air, then weight of the object in water. There is another definition. This and all you have to know. Clear? Right? So somebody asks you, right, that is, suppose this is an extra topic I am giving, okay. Suppose someone is, or somebody, right, it weighs around W, right, it weighs W in air, right. Its weight will not be same in water, right. Let's say its weight is W1 in liquid, some liquid, right, W1 in some liquid, and it weighs W2 in water, right. Object you would have seen, right, as you can see that when you come, or an object inside water will be weighing less, right. So weight differs, right. So let's say there is a body, it weighs W in air, W1 in liquid, and W2 in water, right. Then relative density can be depicted as relative density, right, is equal to W minus W1, that is weight loss, right, of the object in liquid divided by W minus W2, that is weight loss of the object in water, right. Mug up the equation, guys. You just have to write. So if you want, I can write here loss of weight in liquid by loss of weight in water. This is also a equation for relative density. Relative density you have already learned as density of that object in liquid, or density of that object, right, by density in water, or density of water. When you compare the object's density with the density of water, it is usually known as relative density. Now there is another way you can say, when you are not given anything regarding density, then you can say if that object is in air, it has another weight, in liquid it is having weight W1, in water it is having W2 weight. Means if someone asks you relative density, you can just find loss of that object's weight in liquid by loss of that object in, or loss of the weight of the object in water, that is also relative density. Clear? Now this much is the extra section initially I wanted to introduce while learning the topic mechanical properties of fluids. Now the next topic which we are starting is pressure. So as I told you, this is the starting point of mechanical properties of fluids as per your NCERT textbook, right. This is something you know. So what is pressure? Pressure is the result of a normal force applied on an area, right. Normal force is very important. So you would have learned, or in your textbook itself you would have seen that pressure is defined as force per unit area. But actually what type of force is acting? Because fluids can only exert force normally. Let us suppose this is an object inside the liquid, then when you compare a unit area on which the force is acting, it is always normal to that area. See, for this area this is normal, right. So a liquid always exerts force normal to that area. So that's why we say pressure is the result of normal force applied on an area. Clear? So if that force is acting on a small area, right, so the force will be also small, right. So I can say it is dF, small force by small area. Or you would have learned for this section, you can even say when limit delta A tends to 0, it is delta F by delta A. You can even write it like this, right. So commonly when the force is uniform, right, suppose the uniform force is acting, it is not varying that much, then you can just say pressure is equal to force by area. This is something which you have learned, right. So you can see that force is a vector, right, but pressure is a scalar quantity, right, because it is always having one direction only, right. It is always normal to the area. If whatever area you consider, pressure always, or the force here is always acting normal, right. So the pressure is due to a normal force, so the direction is always constant, hence pressure is a scalar quantity, right. So what is the unit of pressure? You would have learned unit of pressure is Pascal, right, or I can write this 1 Newton per meter square, right? And what is its dimensional formula? ml raised to minus 2 T raised to minus 2, right? And you would have heard about other units of pressure, right? That is atmospheric pressure at sea level, and 1 atmospheric pressure is equal to 1.013 into 10 to power 5 Pascal, right? And there is another used, you can call it as torr, right? 760 torr. 1 torr is equal to 133 Pascal, right? Or there is another unit, pound per square inch, right? That is 14.7. That is this one, not this one. This you can make it in a bracket. 1 torr is equal to this much Pascal. 1 atmospheric pressure is equal to 14.7 psi, that is pound per square inch, right? This and all are units of pressure itself, right? 1 atmospheric pressure, Pascal, right? So this and all are units. Good to know things, guys. Clear? Similarly, you would have seen 1 atmospheric pressure definition you would have seen as the pressure exerted by a vertical column of mercury of around 760 mm tall. That you have learned, right? And you would have heard about the unit 1 bar, that is equal to 10 to the power 5 Pascal, right? That is equal to 750 torr, right? And 1 torr is actually what? It is a pressure exerted by the same mercury column, but of how much mm tall? 1 mm tall. This is not all a good thing, guys, right? Clear? So some of the things you have to know, some of the examples which has been depicted in your textbook also, right? Suppose you are having a sharp needle, your injection needle, and you are having a pencil, right? Which one exerts, you are applying same force here, right? You are saying giving same force here. This is an area here, right? Which is going to cause a lot amount of pressure, this one or this one? Obviously this one. Why? Reason is here the tip is going to cover a small area only, whereas here the tip will cover a larger area. So you know pressure is equal to force per unit area. So area, how much it decreases, that much increase in pressure, right? So you can see in this case the area is very small, that's why the pressure is higher. Whereas here the area of contact, right, where the force is exerted is larger, hence the pressure will be small. So which one is the syringe is having higher pressure exerted? Clear? Right? The greater the area, less is the pressure, and vice versa. Clear? So obviously greater the force, that much increase in pressure. Clear? Right? So the two force factors which determine the magnitude of pressure is force and area. Then in this example you would have seen that the stuntman will be lying on a bed of nails, right? Right, means that he is having a large number of nails on a rectangular slab, and all nails will be identical and they will be of equal height, right? We see that a man is not feeling any pain and he is lying comfortably on the bed. This is because there is a large number of nails and all the nails are closely placed towards each other, right? All the small pointed nails make larger surface area throughout this one, right? And therefore the weight of the body is compensated by the entire area of the nails, right? Clear? That is, individual nail is not contribution. All nails are so closely packed that they form a uniform area, right? And the surface area increases means obviously the pressure decreases. That's why he can lay on it. If it had been like this, one needle here, one needle here, one needle here, one needle here, it would have pierced him. Clear? Right? So this is a very good example of depicting how pressure is affected by the amount of force applied and area of contact. Clear? Now let us move on to a small problem I wanted to discuss. Suppose there is a 50-kilogram girl, right, and she's wearing heel shoes, right, and she's balancing on a single heel. The heel is having a circular section and its diameter is 1 centimeter. So what is the pressure exerted by the heel on the floor? That is a question, very easy, right? So 50 kilogram is the mass, diameter 1 centimeter means it is around 0.01 meter, right? So radius will be how much? It will be half of it, that is 0.05 meter, right? So area of the heel will be what? A is equal to pi r square, right? So pi r square, so it will be pi into 0.005 whole square, right? You will get it as around 7.85 into 10 to power minus 5 meter square, right? Clear? And you are asked what is the force exerted by the heel, right? So force is equal, sorry, pressure. So you have to find force first. That's why then you can find force by area, mg, right? So 50 into 10, that is 500. So the force applied is 500 Newton, right? So for pressure will be force per unit area, that is 500 divided by 7.85 into 10 to power minus 5. So you will get around 6 point something into 10 to power 6 Newton per meter square, right? I have not calculated the correct values. It's easy, you can do it like this. In the entrance questions, you can make this as 8 and this becomes 10 to power minus 5 goes up and you can make it as 10 to power 5. Then 50 by 8, you can take it as 48, right? So 48 means there is 6. Then there is 20 means 3, right? Clear? So 20, then 3, then again 20, so 3 goes off, right? 63.3 into 10 to power 5, or you can write 6.33 into 10 to power 6, right? So you will get this as answer. Clear? Right? So this is something you have to know about pressure, right? Now we are going to talk about pressure in fluids in detail, a little bit more. That is the next topic as per your textbook. Clear? So what is a force? It is a normal force exerted by the fluid per unit area, right? This much is clear, right? And the other sections, I wanted to introduce a small problem again. So I saw just a good problem. So two thigh bones, that is your femurs, right? Each are having cross-sectional area as 10 centimeters square. They are supporting the upper part of the human body, right? This is your two legs, right? This is thigh bones, right? These two femurs are having this much area, right? And the body of mass is how much? 40 kilogram mass it has to balance. So what is the average pressure sustained by it? So obviously, how would you do it? You have to find the total cross-sectional area, right? Then you have to find mg. Then you have to just find mg by A. Then you will get the average pressure. Yeah, so you already given the area section, right? And there are two legs. So the total area will be two cross-sectional area. So it will be 2 into 10 to, right, centimeter square. Then you have to convert this into meter square, right? Then this will be 400 Newton F. So you can just do this one. I just wanted to make you understand when there are two legs, then you have to consider both of their cross-sectional area. Clear? Right. So next section, before going to the Pascal's law, okay, we'll go to the Pascal's law itself. Then we'll go for a variation of pressure with depth. Clear? So what does Pascal's law state? Pascal's law states that in a, suppose I'll go for the statement, right? Then I will explain it throughout, right? Suppose if the pressure is applied to uniform fluids that are confined, the fluids will then transmit the same pressure in all directions at the same time or same rate. I'm explaining the law. This law has to be by hearted, guys, as it is, right? It states that if the pressure is applied in uniform fluids that are confined, the fluids will then transmit the same pressure in all directions at the same rate, right? See, this is simple if you understand this concept. That is, if you are having a box, let's say like this, and you are having liquid which is incompressible, means it cannot be compressed, right? So when you give a pressure, right, at this point, then let's say this pressure, This P will be carried forward by every section. That is, if you measure pressure here, then also the pressure will be P, and if you measure pressure in this point, there also the pressure will be P. So I'm stating the statement again. The pressure, if the pressure is applied to a uniform fluid which is confined, right, this is confined inside this container, right, then the fluid will then transmit the same pressure in all directions at the same rate. I hope you understood, right? It is very easy to understand Pascal's law, and it is usually asked again and again. Clear? Right? See, I'll explain it with an example also. Right? Suppose there is a vessel, right? It is filled with liquid, or let's say with water, right? Which is uniform throughout, and there is only one type of fluid, which is water. Consider the vessel which has oil and water, then it is not uniform, right? Suppose there is another container, it is having both water and oil, right? So this will be a mixture of oil and water, right? So fluid should be confined means that the fluid is present within the region in space, that is not allowed to spread, that is not allowed to spread. So that is the first statement, right? So in this condition, right, you are not supposed to use a mixture, because both of them are, even if they are immiscible, that is difficult. Even if you use immiscible liquid, it is better you use a single fluid. So then two conditions we have to make sure you are understanding. One, the fluid should be uniform, right? Then second, it should be confined in a space. Then only you can use the Pascal's law, right? So this is a major criteria. The example section which I was talking is, suppose there is a balloon, right, and it is filled with water, right? When we press it hard against the wall, suppose this is a wall, right, then we'll see that the shape of the balloon changes, right, tries to go outside, right? This is because we apply force on balloon and the pressure is exerted, right? You're exerting pressure on the balloon. So water is uniform fluid, it is confined in this balloon and is not allowed to spread. So when you apply a pressure at this point, so each and every point of the balloon will get, I'm so sorry, I forgot to make it in silent, right? So every point will be having the same pressure, right? So by the same pressure only, this section also, all of them are having same pressure at the same rate. That's why when you exert the pressure, these each points are getting same pressure, hence it is having a condition to break it. Clear? I hope you understood. Right. Now, in order to make you more understand, let us say we are going to take a vessel like this, right? Right. Right. Let's say there is an opening here, opening here, opening here, opening here. Right. So I'm having a device like this. Let's say there is a piston. I hope you all know what is piston, which can move inside and outside, and it can block it here, right? Similarly, there is another piston here, can move to and fro. Similarly, a piston here, and there is a piston here. Right, you can move it again and again. Right, say this is a point A, right? So let us say we are applying a force on the piston A. The piston is, say, let's say 4 openings are there, right? So the entire openings, 4 pistons are attached. Let us say I am pulling. First I pulled out, right? Then only you can push in, right? So I pulled out and then I pushed in this piston. So the piston moves downwards, right? So I am exerting what is known as pressure. Let's say this is filled with water, that I forgot. Let's say this entire thing is filled with water, right? So the water now has got a pressure, right, which is due to this piston's movement, right? Now the piston moves downwards, a pressure has been exerted at this point, right? This pressure will be entirely distributed, right? So we will see that except this piston, all other pistons will move outwards, like this, right? Why? You only exerted pressure at this end, right? And you have exerted pressure on the liquid. So why does this piston or this piston or this piston move outward? Because the pressure which you have applied at this end has been transmitted as it is to this point, to this point, and this point. Hence the piston moved outwards. Clear? So moving of A inwards caused the other pistons to move outwards. This is the example which depicts Pascal's law better, right? So for a uniform liquid, that is something which you can conclude, right? For a uniform fluid in equilibrium, the pressure is same at all points in a horizontal plane. Thus, there is no net force acting on the fluid. The pressure is same at all points, right? It is even you can say that the fluid is moving because due to the presence or difference in pressure. That is, a fluid will always move from a point which is having higher pressure to lower pressure, right? That's very easy to understand. Why? That's why you can say the higher point, right? Higher point to lower point, right? So I can say higher potential energy, so I can say there is high pressure at this point and this is low pressure, right? So that's similar. I can say you use a pump to pump water from this point to this point, right? So you're exerting higher pressure here, so from higher pressure to lower pressure the water can move, right? Right, so if you even example take the wind, right? So the wind is nothing but moving air. So air is a fluid. So the air moves from the region from however which that is you have learned in geography. It moves from higher pressure to lower pressure, right? So air is that type of fluid itself. You can consider because it's a mixture, right? Clear? So it is very easy if you understand this much concept, guys. I have not introduced that much of details. It is very details means I have talked a lot about the theory sections, which you know, right? Now we are going to come in terms, or we are going to talk about pressure in detail, right? So this section is very important. Clear? Next section or next topic which I am going to take is not there in your textbook as it is explicitly is not there, but I believe this section if I take it is better, you will understand, right? So okay, first let us talk about pressure due to a fluid column. Pressure due to a fluid column, right? So that is, I will explain what it is. Suppose I consider there is a vessel and I filled it with some fluid. So this fluid will be exerting pressure at the bottom of the vessel as well as it will be exerting pressure on the walls, right? So I'm going to consider that this vessel is having cross-sectional area, let's say A, and let's say the liquid which is present here is having density rho, right? And this liquid has been filled till the height h, right? Then the weight of the liquid which exerts a force at the bottom is equal to what? It is volume into density into g. That is something you have to know, right? Mg, right? See, so the weight I can write it as what? Weight is equal to mg, that is the weight which is experienced by the bottom of the tank or the container. I can write mass is equal to volume, then it is into density into g, right? I can write like, so this is the weight of the liquid, right, which exerts a force at the bottom of the vessel, right? This is the weight. We can write it like this, right? Right, this much is clear, right? And this volume I can again write it as volume is equal to area into length. Here I can write area, right? And length here is how much? The column's length, that is h, right? And then I can write rho and then I can write g. So this can be written as a final equation for the weight, right, of the liquid which is exerting a pressure or a force at the bottom of the vessel, right? And this force is acting uniformly at the bottom, right? So someone asks you what is the pressure exerted by the liquid on the on the bottom of a container, then pressure is equal to what? Force per unit area, right? right? So force is this is the force, that is a weight, that is A H rho G by A, or I can just write it as H rho G, right? It is a very general equation, right? It is, there is a liquid which is there inside a container. The pressure exerted by the liquid is equal to, at the bottom, is equal to H rho G, right? All the points in the liquid at the same depth, right? Suppose there is a liquid container section, so all the liquid, right, all the points, right, all the points of the liquid at the same depth, because they are at the same depth means they are at the height h, right, will have the same pressure H rho G. The next topic which is there in your NCRT and very important section for continuing this topic of pressure is variation of pressure with depth. Variation of pressure with depth. Okay. Now, how this is a calculation part, guys, and it is a derivation part also, right? Suppose we are going to consider this is a liquid section filled with some liquid, right? And you are going to keep a cylindrical object inside this one, right? And then this fluid is completely inside this container, right? And there are two different positions I am going to consider. Let's say this is the first position, this is the bottom section is the second position, right? Now let's say the fluid is at rest, right? So the force will be on the vertical directions only, right? There is no horizontal direction force because the liquid is stagnant in nature. Now, so let us only talk about vertical conditions, right? The forces on vertical conditions means at the top sections, right? Let's say this force is F1, right? At the bottom section, the force will be in this direction, right? That is F2, because that is how you say it is perpendicular to the area, right? So F1 is downwards, F2 is upwards, right, from the bottom, and F1 is at the top bottom, right? So F1 and F2, this much is clear, right? So at the top section, that is F1, can be written as pressure into area. So let's say the pressure at the top face is P1. So I will say P1 into A, and this downward in direction, right? P1 is the pressure at the top face. Okay. Similarly, I can write F2 is equal to P2 into A. That will be from down to up, right? And P2 is the pressure at the bottom surface. This much clear, right? So the net force someone asks you, right? Let's say the downward direction is negative, right? Let us say downward direction is negative, means the total force, net force will be what? Minus F1 plus F2. I can take it like that, right? F2 is in I'm taking it as positive because upward direction I'm taking positive, downward direction I'm taking as negative. This much clear? So net force, I can now write it as minus F1 means it is minus P1A plus P2A. I can take A as common, so that I can write it as P2 minus P1 into A, that is net force, right? I can write it like this, right? Now the net force will be balanced by what? The upward force and the downward force will be balanced by the weight of the object, right? So at equilibrium condition, I can say the net force on that cylinder is equal to mg. There is a weight of the cylinder, and that is actually equal to the weight of the liquid displaced, right? Clear? And what can I write about mg? I can write it as V. Remember, volume into density into G, V rho G, right? Where rho is the density of the fluid, right? Why did I write it fluid? This rho is not the density of this material, right? How much will be the weight of this object? Right, at weight of the object will be equal to the weight of the liquid it has displaced. This you would have learned about it in your lower classes, right? Eureka, Archimedes principle, right? So if you want to measure the weight of an object inside a liquid, you just have to measure the amount of liquid it has displaced, right? Clear? So mg, I will write it as V into rho into G. V is the volume displaced, rho is the density of liquid, and G is acceleration due to gravity. This much clear? And I can write V is equal to area into height, right? Area into height. Let's say the height is h. This one is having height h. So area into height into h. So ah rho g, right? Clear. So this F net I have written as P2 minus PA. So that is P2 minus P1 into A is equal to AH rho G. AA cancels out. I can write P2 minus P1 is equal to H rho G, right? That is the earlier diagram you had this one, right? This, right? So if you consider this condition, this P1 is the pressure at the above surface and P2 is the pressure at the below surface. Pressure difference at a height P2 minus P1 is equal to height of the liquid column, right? You can consider this cylinder as a liquid column itself, right? Because it is occupying the area where there had been a liquid column, right? So P2 minus P1 is equal to H rho G, right? So that means this is just like this one. It is, you are not considering a cylinder there. Suppose there is a liquid, it is tightly spaced. I am going to consider an area like this, not a cylinder, guys. Now I have considered just an area which is looking like a cylinder, and I can consider 2 points at this area that is having pressure here P1 and there is a pressure P2 here, right? Then the pressure difference between these two points is equal to H, height difference between these 2 points, into density of the liquid into G. That is the importance of this equation, right? Difference of pressure between 2 points separated by a depth h is equal to P2 minus P1 is equal to H rho G, right? Clear? Right. Now this top cylinder or the top portion, right, is usually exposed to air, right? You can just consider that the scenario is not like this. There is a water column like this, right? And you are considering in the area like this, right? So this becomes the top section. So usually this P1 point is atmospheric pressure, right? So I can even write this one as P2 minus PA is equal to H rho G. Clear? Right? Or P2 is equal to, we can write this one as P2 is equal to PA plus H rho G. You can even write it like this. That is, if you are considering a liquid section like this, let us not consider a cylinder section. Let us have a container. It is having liquid like this, and you want to find the pressure at this point. Pressure at this point is equal to, right? Let's say this point is at a height h from the surface, right? So pressure at this point is equal to atmospheric pressure plus h into density of the liquid into G. That is the meaning of this equation. P2 is equal to PA, that is atmospheric pressure, plus H rho G. Is much clear? So pressure P at a depth below the surface, right, below the surface of a liquid open to atmosphere is greater than the atmospheric pressure by an amount H rho G. So they always, as you go down a liquid column, the pressure always increases. Clear? Right? So this is a very important criteria, guys, right? Clear? So if you, okay, before going to the problem section, I would have to continue the theory section itself, then we'll go for a problem section itself. Next, I want to talk about hydrostatic paradox. Hydrostatic paradox. This and all are there in your textbook, guys. This and all are your textbook topics itself. Hydrostatic paradox. Hydro means obviously water. Static means wait, at rest, right? So paradox means something which is no taking place surprisingly. It doesn't happen actually. You don't think it will be happening, so but it happens. That is this. I will explain it with an example. Suppose I am going to consider a vessel like this, right? I am having a vessel like this. Okay, right. And there are different shapes. Okay, one is rectangular, whatsoever shapes, right? So let's say this is C, this is B, and this is A, right? And we have a source from which the water enters the three vessels, right? Water enters through a horizontal base like this. Let's say it is entering, right? And these vessels, we observe that the water is rising, right? The water has risen, okay? And we see that all of them are having same level of rise, same height, right? Irrespective of the shape or size or shape, right? All of them are having equal level. What you would think, ah, this is narrow, so it will be having higher level, this is broad, level will be lower. No, you will see that all of them have the same level, right? This is because the pressure at the same point, right, at the base of the level, right? Let's say that is I am having a pressure at this point P, means this point also have pressure P, this is also having pressure P, this is also having pressure B, right? So the water will rise in all the three vessels till the pressure at the top of them is same as that of the pressure at the below. That's the meaning of it. See, if the higher, see, this is like this. Suppose I have a container like this, I am pushing water, means here the pressure will be higher and here obviously is a constant pressure which is lower. So it will be rising again and again, right? So what happens here also, I apply a pressure P itself. So at that point, no more rising is allowed, right? So I will say when upper pressure and lower pressure, when it equals, then only the water rising stops. All right. So we know all the levels in this picture. This is having pressure P, this is having pressure P, this is having pressure P, and all of them are open, right? So all of them will be having an above atmospheric pressure PA, right? So all of them will see a rise in level till PA and P equals, right? Till then only the water will be rising. So one moment, all of them, when you are having same pressure, right? Because PA minus P, let's say that is, P minus PA now. P minus PA is equal to H rho G. You are having same liquid, you are having same acceleration due to gravity, right? And you are having same PA and you are having same P, means obviously you will have same H. Clear? This is hydrostatic paradox. Clear? Right. I hope you understood. Right, next we'll go for the next topic straight away, because I want to introduce some of the terms which you have to know about. One, which is atmospheric pressure, which you have learned earlier itself. So atmospheric pressure. So what do you mean by atmospheric pressure, which you depict as PA? It is a pressure exerted by the weight of the atmosphere. Right? What is atmosphere? It is a mixture of different gases. All the gas molecules together, they will be having some weight, and this weight is some pressure. And because suppose I am standing, means this atmosphere will be exerting a pressure on me, right? Because it is a mixture of gases, and this pressure is known as atmospheric pressure. And at sea level, as I've told you, it is 1.01 into 10 to the power 5, right, Pascal, right? So that's why one atmosphere, write it as 1 into 10 to the power 5, and usually you would take it as just 10 to the power 5 Pascal, right? And there is a device even to measure atmospheric pressure, and it is known as mercury barometer. You might have learned in your lower classes. I hope you have learned mercury barometer. Mercury, because it is filled with mercury, right? It consists of a trough means it is just like this one, right? So it is filled with mercury, right? What is a symbol of mercury? It is Hg, right? And there is a tube, just like a test tube, right? So there will be a tube which is inverse and it is kept like this, right? And it is also consisting of mercury itself, right? Clear? And it is inverted straight to the trough. One end of the tube is closed and the other is open and is placed in inverted. This much is clear, as you can see in the diagram, right? Now this tube will be having mercury to a certain level, right? And the space above the mercury, this much space, this is full with mercury, and the space which is above mercury is occupied by the vapors of the mercury itself, right? So I can say the pressure can be considered 0 at this place. That's the pressure here is 0, right? Clear? The atmosphere will be exerting some atmospheric pressure on the mercury level. As a result of the level of mercury decreases in the trough and it increases in the tube. Why? See, here the pressure is 0, but atmosphere pressure is exerted over here, right? So this will be PA here. So this is higher than this one. So obviously what happens? According to the increase in atmospheric pressure, the pressure here also will be PA, right? So this pushes the mercury level inside the tube. Right? Clear? This much is clear. So what happens? The mercury level inside the tube increases, whereas the trough's mercury level decreases. And increase in the level will say how much pressure has been exerted by the atmosphere. Right? Clear? And the pressure exerted is directly proportional to the increase in the mercury column of this tube. Right? So we can say, suppose we are considering the level rise as H. The level has increased to H, means P atmosphere is equal to Y. You know this lower position is having what? Pressure PA. That is, I'm going to write it as P atmosphere, or I can write it as P itself. That is atmospheric pressure minus topmost pressure is P is equal to H rho G. This much clear? But we know at the topmost position here it is 0. So I can write PA is equal to H rho G. So you just have to measure the height of mercury column, which is H, which is usually in mm, okay, into density of mercury into G. Then you can say how much is the atmospheric pressure. This is how you use a mercury barometer. I have talked about the units of atmospheric pressure or units of different pressures, and please write it down by yourself now. Clear? Right. Now the next term which I want to know or make you guys understand is gauge pressure. Gauge pressure. What do you mean by gauge pressure? See, pressure difference between the system and the atmosphere, that is known as gauge pressure. Why it is called gauge pressure is usually when you use a device to measure the pressure of any liquid, what you measure is called gauge pressure. I will tell you like an example. Initially we found that suppose there is a column like this and the bottom is, let's say, P, which is at a height H from top position. So this point P is, let's say there is a point and it is having pressure P. That is better. We are going to consider this point and it is having pressure P. This point is having atmospheric pressure, right? And we found that P is equal to, pressure at any depth is equal to PA, atmospheric pressure, plus H rho G. We have found that one, right? P is the pressure at any point, right? And PA is the atmospheric pressure. This much clear? We can see that pressure at any point is always greater than the atmospheric pressure by amount H rho G, which is, I have taken it again because I want to refresh it again. Okay, now I have written like this also, P minus PA is equal to H rho G. I have written in this form also, right? So here this P is called the pressure of the system. Right, the pressure you want to find. You want to find the pressure at this point, right? So this P is called pressure of the system. PA, that is your atmospheric pressure. So PA minus PA is the pressure difference between the system and the atmospheric pressure, and this is called gauge pressure. Clear? I hope you understood. It's very easy to understand. Actually it is something which I could have taken in that section itself, but I wanted to don't mix up a lot of things, because after this you have to talk about absolute pressure also. So what is PA minus PA? Sorry, P minus PA. P, that is a pressure at any point, that is called actually system pressure, pressure of the system. PA is the atmospheric pressure. The difference between the system pressure and the atmospheric pressure is called as gauge pressure. And any device you use to measure pressure, suppose you are having a gas line and you are asked to measure the pressure of the gas here. So you will connect a gauge, you will connect a measuring device here. So that measuring device always measure a pressure between a point here and the atmospheric pressure. It doesn't actually give exact the pressure or system pressure. It gives the pressure difference between the pressure at some point and pressure at the atmosphere, right? That's why it is called gauge pressure, because gauges always show this pressure. Clear? Right? So any device you use to measure pressure, it always shows which pressure? It always shows gauge pressure. Clear? And just like measuring atmospheric pressure, there is a device which is used for measuring gauge pressure, right? Almost all the devices measure gauge pressure only, right? And that type of device is called open tube manometer. Open tube manometer. Clear? What and all are the parts of a YouTube manometer? Sorry, not a YouTube manometer, open tube manometer. So open tube manometer consists of a a spherical bowl like section, or you call it as bulb, right? And it is connected to a YouTube manometer like this. We have talked about, oh no, manometer is a device which is used for measuring your pressure. It is supposed to look like a uniform section, but pardon me if it doesn't look like a proper tube. I hope it looks like a tube. This section is called U-tube, and this is your bulb section, this one, right? Clear? Okay, moving on. So this section, this bulb section has no as a stopper like section. Then if you want, okay, let's say connected, this is stopper, this cannot be, this can be opened and closed, right? And you are having, let's say, a line and a gas is flowing through it, right? Let's say that gas is having a pressure P, right? I want to measure this gas pressure. Let's say this, and this end of the U-tube, this one is a U-tube, this end is open, so this pressure here will be atmospheric pressure. This much is clear? Simple. Now I want to measure the pressure of this gas, means I will connect this end here, and obviously this will be open, right? So this is open, right? This will be open, and then this will stopper will be open, right? So this straight connection, right? So this, it's a gas, right? It flows through here, blah 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 blah. So here entire pressure will be P, and then it's traveling. Okay, I forgot to mention something. You have to fill this U-tube with what is known as mercury. Yes, yes. So initially, say, let's say this was open, this U-tube was not connected. So this end will be having atmospheric pressure, this end will be also atmospheric pressure. So this level and this level would have been same. Yes. Now I have connected, right? So this gas is pushing this column, right? In the left arm, the pressure increase, so this column will be falling down and this column will rise above, right? Let us change the height level to this much, right? Initially the position was here, right? Let's say this position as A, right? So that this A position, this position had, so let's say the pressure was P, then this pressure also will be P. Now when you added or made this gas to enter, means this gas pushed this column downwards and this column moved upwards. This much easy? Yes. So now when the gas has reached here, means this pressure over here is P, right? And this pressure that is in the left column, right? At the left column the pressure is P. Yeah. At the right column the pressure is not P, right? Now, so let's say the rise in the mercury level is H, right? Initially it was supposed to be this level, right? The rise in level is H, right? Clear? So this position, if it is P, right? So you know at same position, same pressure. So this position also has pressure P, right? So this much column has caused a pressure of H rho G, right? Remember, a pressure inside a column, right, is H rho G. So this much depth pressure is H rho G, right? So I can say the left column, this one, left limb, if you want, you can say it as left limb. That is better. So left limb has a pressure of P, right? Whereas right limb will have a pressure of how much? PA plus H rho G, right? PA plus H rho G, because here you want to find the pressure here, right? So it is always greater than the atmospheric pressure by H rho G, remember. So right limb will be having PA plus H rho G. Clear? Right? This much is clear, simple as it is, right? So at equilibrium, right, this much is clear. I hope you this much is clear. So at the right equilibrium, proper equilibrium, you would say this pressure, that is in this column, how much is the pressure, right, that should be equal to the right column pressure, right, at equilibrium. You always place equilibrium condition, very important. So if you want to measure a device, or you are using a measuring device, so equilibrium condition has to be maintained. So the pressure at the left limb should be equal to the pressure at the right limb, then only it stops. Suppose the pressure here is more, then that means the rise will increase at point will exceed and it has to fall down, right? So it has stopped at this level, means the pressure here has been equal to this, right? That is, the left limb pressure is equal to right limb pressure, or I can say P is equal to PA plus H rho G, right? Or I can write P minus PA is equal to H rho G. So PA is something which you can know, that is atmospheric pressure. H you can measure, rho is the density of mercury, G is acceleration due to gravity. So unknown pressure P is your what? Pressure of the gas. Or I can say what is P minus PA? That is the pressure of the system minus pressure of the atmospheric pressure. What you have found is called gauge pressure. Clear? Right? So what is a device which is used for measuring gauge pressure? It is open tube manometer, which is a device which is used for measuring atmospheric pressure. It is barometer, or you can call it as mercury barometer. Clear? So small term which I want to introduce now, last section, which is absolute pressure. Absolute pressure. Right? Absolute pressure is defined as the pressure above the zero value of pressure. That is, suppose it is actually the pressure which a substance has, right? This always, suppose if you have measured this P is equal to PA plus H rho G, right? Clear? And here you call the pressure of system, right? This pressure of system is actually termed it as absolute pressure, right? So P is called absolute pressure. P absolute pressure, or I can so say it as system pressure. PA atmospheric pressure, right? P minus PA is gauge pressure, right? And H rho G is the pressure, generally pressure exerted by a column of liquid, right? Clear? This much is clear. So we can move forward with the next section from the next class, right? So this and all terms, very important sections I have completed today, right? So during your vacation classes, please go through all the chapters, right? So till now I believe we have completed more than 8 chapters, right? Gravitation till gravitation, till mechanical properties of solids, right? So a lot of chapters has been completed, so please go through them and study, right?